Hello dear students, this time we are trying to share with you one more video, one more lecture. It is on this differential equations of first order but of higher degree, but of any degree, but order will be first. I take it for granted that you already know about the order and degree of differential equation. You did it in your starting concepts of this differential equation, because without order and degree you cannot go ahead. Still, I would like to have this. Suppose you consider the differential equation of this form. You have d2y dx square plus 3x, say it is dy by dx raised to power 5 plus 6y is equal to 0. Suppose it is a differential equation before you. What is it? Is order. Order means the highest derivative, the highest differential coefficient involving in the differential equation. So it is order is actually, order is second. What is it? Is degree. Degree is not 5. Degree is the exponent or power of this highest order. So it is order, it is degree is 1. So we say it is of degree 1. So this differential equation is of order second and of degree 1. Similarly, if you have differential equation now of order 1, that means order 1 differential equation, when you have order 1, it will involve dy by dx. It will not involve d2y by dx square. It will not involve d3y by dx cube. No, it will involve dy. And of higher degree, say it can have dy by dx raised to power 3 plus dy by, say 3 times dy by dx square plus 4x something equal to 0. So we say this is of order first and degree is 3. Order first and degree 3. So when we say order first will involve dy by dx, and of any degree it will involve the powers of dy by dx. And in this case we will also introduce here what we mean by this solvable for p. Let me first introduce a differential equation with variable coefficients I am taking of order 1 and degree any. Let us consider. We consider here a differential equation. Let it be psi naught xy, it is some function of xy, dy by dx raised to power n plus psi 1 xy dy by dx raised to power n minus 1 plus psi 2 xy dy by dx raised to power n minus 2 plus so on. Let it be psi n minus 1 xy dy by dx, then plus it is psi n xy is equal to 0, where this is some function of xy, this is function of xy, this is function of xy, this is also function of xy. Okay, and this is here some function of xy. We do what? We put here in this differential equation dy by dx is equal to, say, p. You observe this: order 1 degree n, order 1 degree n minus 1, order 1 degree n minus 2. And what is the highest order? Highest order is n. So it is of order 1. Highest degree is n. Highest degree is n. Order is 1. It is of order 1 degree n. If we put dy by dx is equal to p, what will be the position of this? It is psi naught xy. This will be your p raised power n plus psi 1 xy. This will be your p raised power n minus 1 plus psi n minus 1 p this is plus psi of n xy is equal to 0. Now you can say this is the differential equation of order 1 degree n involving p. It is nth degree in p. Now we can say it is nth degree in p. If it is nth degree in p, we are certain here this coefficient of xy, this should not be 0, because if it is 0, then this equation ceases to be of degree n. If it is of degree n, this is not 0. So we can divide throughout by, say, psi naught xy. It is some function of xy. What you get? You get psi naught. Here you will get it will take the form Pn plus psi 1 some function of xy by psi naught xy p of n minus 1 plus psi n xy n minus 1 by psi naught xy. Then this will be psi n xy by psi naught xy is equal to 0. I am dividing. Why I am doing so? Because I want to have coefficient of p raised power n1, so that I can use the factor theorem here. When it has the n factors, I can write this equation as the product of linear factors. This is your factor theorem that we derive from the fundamental theorem of algebra. Okay, now I can say this is some function of xy, this is some function. Here you will have a some function of xy, some function of xy, some function of xy. I can write this in this way also. I will put it in this form. I can put it in this form. Let me write it now. P raised to power n plus, say it is a1 xy p of n minus 1 plus a2 some function of xy p of n minus 2 plus so on. This is here your p, this is p here. Right, plus a n minus 1 xy p, then plus it is a n xy is equal to 0. This is equation number, you can name it, say it is first. This is your equation number 1. You see the coefficients are some function of xy, some function of xy, some function of xy, and a n xy is also some function of xy. This is a nth degree. This is now nth degree in p. It has the degree n p. P is itself linear. It has nth degree. We assume let alpha 1, alpha 2, alpha and b n roots of first, where each alpha I is some function of x and y. These are functions of x and y. Well, what you do is you can write it as factors. You have it as factors p minus alpha 1, p minus alpha 2, p minus alpha 3. It is p minus alpha n is equal to 0. These are the factors of this equation. Now when you take separately 0, it is p minus alpha 1 equal to 0. It is p minus alpha 2 is equal to 0. This is p minus alpha 3 is equal to 0. So on to p minus alpha n equal to 0. Now this will be a linear differential equation. It is what? Linear differential equation. It will be some differential equation, first order, dy by dx, either by variable or separable or some this method. You will get the solution of this differential equation. Dy by dx, it is a differential equation of first order, first degree. differential equation of first order, first degree, and you can have the solution. When you write dy by dx some function of x, say you will have a solution in of the form assuming it is solution be some function of xy, it will involve some arbitrary constant 0. This will also have a solution some way or other way, variable or separable, say py by px py by px plus dy by dx plus py is equal to q, that is linear differential equation. In some way you will have a solution of this differential equation. Let us assume that f of 2 some function of xy c2 is equal to 0. Then this is also a some linear function, some differential equation in first order, and by previous methods that you did, you can solve with this. It will have some solution of the form f of xy c2, and we assume this has also a solution. Let its solution be of the form f of xy cn equal to 0. We are assuming we can solve this. These are now differential equations involving dy by dx some function of xy, sometimes variable separable, sometimes other ways that you did previously. You can have the solution. That means when I put these solutions here, I can write now the solutions is are that means I am assuming their solutions will be of this equation like this. As you assume, it will be some function of xy f1 xy c1 into f2 xy c2. I am replacing each factor by its solution in other way. If replace each factor by its solution, f3 xy c3 fn xy cn equal to 0. This is the solution. But in this solution we say it is not a complete, because it involves the different constant c1 here, c2 here, c3 here, cn here. Actually our differential equation is of first order. The number of constants involving in a differential equation depends upon its order. If it is of order 1, it will have only one arbitrary constant, like you have solved say variable or separable of first order, you have solved dy by dx py is equal to q, linear differential equation of first order, you have Bernoulli's equation of first order. There you use only one constant. In case you have a differential equation of second order, say it is d2y dx square plus 3 dy by dx plus say something 3x is equal to 0. It is a differential equation of second order. It will involve two constants, different constants c1 and c2. It will involve two constants. Okay, but our differential equation being of first order, it will have only one. This constant. It is a first order. So this c1, c2, c3 are not different here. This implies differential equation first being of first order. It is of first order. When it is of first order, that means our constants cannot be different. It is one and the same. c1 is equal to c2 is equal to c3 is equal to cn. It is same is equal to c. Suppose we suppose that all these are same, let they be equal to c. So what is our solution then? Our complete solution will be now this is f1 x y c into f2 x y c, then into f3 x y c, so on to fn x y c equal to 0. This is the complete solution of this differential equation, which is of first order and any higher degree. You have seen here what does this p stand for. Actually it is dy by dx, and this is also why we name the equation solvable for p. So I have given you the solution, how we find out the solution in this way. This is a crux of this result. Now we have different forms of this type of equations. We have in fact different types. We have one type is when we have differential equations which are purely solvable for p. Then we have differential equations solvable for y, solvable for x, and there is some more case when x is absent, p and y is present. When y is present, p and x is y is absent, p and x is present. And then differential equations which are of Clairaut's form. In this form also we have the Clairaut's form. Okay, I will just have some applications. Let us have applications. Some applications. Application I will take first. Solve the differential equation simple case p square minus 5p plus 6 is equal to 0. You want to solve this. P square minus 5p plus 6 is equal to 0. P has its usual meaning, as you would say, it is dy by dx. You can solve this. It is solvable for p. It is 3p. Factorize it. 2p plus 6 equal to 0. Its factors will be p minus 2, p minus 3 is equal to 0. Okay. Now how we proceed? Let us see. You have p minus 2 is equal to 0. This gives you dy by dx is equal to 2. This is dy is equal to twice dx. So when you integrate it, these are here you have variable separable. When you integrate this, it is y is equal to 2x plus c. That means y minus 2x minus c is equal to 0. C is the constant. But we have to use same constant here as we said previously. It is of order 1. It is 0. So p is equal to 3. This will be dy is equal to 3 dx. And on the basis of this, we get y is equal to 3x plus c. This is y minus 3x minus c is equal to 0. So what is general solution of this? Solution of equation number 1. Solution of equation number 1 will be now y minus 2x minus c into y minus 3x minus c is equal to 0. This is the solution. This we have come to know what we mean by this equation is solvable for p and how we find out the solution. If it is solvable for p, then solvable for p means when you can find out its factors easily. Then give the value to p dy by dx with either variable is separable or some other method. Let us have some one more example here. Suppose I have a question here. Suppose you want to solve the differential equation. Say you want to solve, it is a p square minus 2p hyperbolic function cos x plus 1 is equal to 0. It is also solvable for p. You want to solve it. I can write it. It is p square minus 2p e raised power x plus e raised power minus x by 2 plus 1 is 0. It is p square minus e raised power x plus e raised power minus x. P plus 1 is 0. It is now again quadratic in p. It is quadratic in p. You can solve it easily. What is its solution? You can write it is p is equal to e raised power x plus e raised power minus x plus minus under root of e raised power x plus e raised power minus x square minus 4 by 2 into 1. This you can write p is equal to e raised power x plus e raised power minus x plus minus. What is this actually? This is your a plus b whole square minus 4ab. That comes out to be a minus b square. Okay. This is a minus b square. When you have a plus b whole square minus b, this is your 4ab minus 4ab minus 4ab. A plus b whole square minus 4ab. This is a minus b square, because this is your 4. What is your ab? It is e raised power x, e raised power minus x. That is 1. So it is a plus b whole square minus 4ab. So that means I can write it only e raised power x minus e raised power minus x by 2. This gives me p is equal to, when I take plus here, it is my e raised power x. When I take minus here, it is p is equal to e raised power minus x. Now you simplify this. This is dy by dx is e raised power x. This is dy by dx is e raised power minus x. This gives dy is e raised power x dx. It is dy is e raised power minus x dx. Okay. And when you, this is a variable separable easily. So